All right. Scroll down, scroll down. All right, so today we're going to look at 3.5 and 3.6, just briefly. There's not a lot for us to cover, and so we mostly used our time to talk about the examples. So the question is, let's say I walk into a coffee shop and the waiter, the barista asks me, do I want coffee or tea? And then I answer yes. So in like logically English, we could interpret this to be something like, I like both equally and I don't want to choose, like you choose for me. It could be, I want both. Or it could be, I prefer one over the other, but I'm just going to say yes and assume that you're going to give me the last one that you listed. And so this sort of thing in English we can kind of pick up by context, but in logic, it's like we have to have rules that we strictly follow. And so I have some statements that I want us to look at, and so I think I'll just pull them up in the book, so I don't have to write them all out. Page 51. The book, the page numbers don't match the... Okay. So it's these guys. So remember we had practice in breaking sentences down into like P equals this and Q equals this. We're going to do that with these. And so for each one, break it down into what's P, what's Q, and then decide if, like, evaluate the truth value of both P and Q. So I'll do the first one for you. So for number 1, 5 is greater than 1, or Lincoln was the U.S. president in 1800. So 5 is greater than 1 is P. Q is Lincoln was president in 1800. 5 is greater than 1 is true. Lincoln was the president in 1800. Let's do some Googling. Lincoln presidency. He was president 1861 through 1865. So the statement that he was president in 1800 is false. I can make a statement. It's a logical statement. That doesn't mean it's true. Okay, so we've got true and false for P and Q respectively. And so number 1 is stating 5 is greater than 1. That's P. So if we write it in a logical expression, we say P, and then we've got the word or. Then we have logical or. And then the next statement, which is Q. And since we know the values of P and Q, it's T or F. T or F is true. Yeah. So this statement is true by logic. All right. Turn to your neighbors and decide what's P and Q for number 2, and is the whole statement true? What's P and Q for 3, and is the whole statement true or false? Go for it. Wait, the arrow is the other way than the or? Yeah. Yeah. That's the,
Or is it something else?
that's V. Is it cap?
Yes.
Wedge. It's wedge.
Wedge. Wedged in.
V is or. Wedge is and is the opposite of or.
Do we use
Kind of.
these cases or not?
But and or doesn't come into either of 2 or 3.
It's the equal arrow is not false.
Yes. Implication.
Oh, it's the
Oh,
but the statement is false. The first one is false.
Here, let me. No. Let me. Yes. Sorry. Let me move this on here. There. Now we've got more space.
Imagine if you were to work on this.
Maybe 30 more seconds. Remember to look up the implication truth tables. And that's on page 41 in the textbook, table 3.2. All right. Are cats birds? So this is number 2. Are cats birds? No. Did Lincoln become president in 1861?
Yes.
And then what's this? What's the symbol for then? The double arrow or implication. Is this statement true or false? True. By our truth table. This is the sort of vacuously true thing. Okay, so this is round 2 of how do we explain this. So the thing is we know the premise is false. We know the conclusion is true. And so here we can't make any assumptions about how this implication, how we got from false to true. So we just say it's true because the ending is true, and so this is a big question mark. But the ending's true. So we say this is true. All right, what about number 3? Was Einstein a physicist? Yes. And then we've got our then word. So true implies, are some men mortal? Yeah? I would argue that all, but the statement is true. I don't know the converse of, is the converse all or is the converse none? I would think maybe none. And so if the statement was no men are mortal, then I would say that is false. But yeah, some men are mortal. Yeah, that's true. So if we have true implies true by our truth table, what does that give us? True. Great job. So this is a type of question that I might give you on the exam. Here's a statement, deconstruct it into this logical equation. I would probably ask that you write P implies Q, and then you say P is false, Q is true, and then the answer is true. And you don't need to guess at that. If you memorize your truth tables, then you'll know the answer. So speaking of not guessing, let's say we've got an equation, or we've got some expression C, and C is this complicated thing of not P or Q implies Q and P. That's our complicated expression. And we want to know, what is the truth value of C? So I can stare at this and break my brain for a little bit, or we can think about it logically. And so this involves kind of like when you're in algebra and you've got this complicated equation and you've got parentheses, so we'll break it down inside the parentheses and make it easier for ourselves as we go. And so the book has some case where they consider like P is equal to true, Q is equal to false, but let's build the truth table instead. So let's say we're looking for P, we're looking for Q, and then we'll break it down into the individual components. So we've got not P there, and then we've got not P or Q, because once we figure out not P, then we know how to do P or Q. And we want to know what's Q and P. And then finally, once we know this implies this, then we can just use our implication truth table to say what's the truth value of C. So we're breaking it into its individual components, and we'll use it to solve the broader issue. Okay, so we know the possible values for P and Q are T and T, T and F, F and T, and then F and F. Those are all the possible values. Not P is we just take this column and we flip it. So that's F, F, T, and T. And then now that we know not P, we can say what's not P or Q. So F or T is T. F or F is F. T or T is true. F, T or F is also true. Right? So now that we've solved one column, we can give it another thing. And then Q and P, we've got P and Q listed out here. And so we just compute the AND operation. So true and true is true. True and false is false. And the rest of these are false, because neither are both true. And so then we can, once we do that, we have not P or Q implies Q and P. And so this is, we just pull out our implication truth table and we say this is true, this is true, and then those are both false. And that comes from implication truth table. So I didn't just make that up, right? That information came from somewhere. And so once we have this truth table, then we can say, okay, I know what the truth value of C could be for any possible value of P or Q. So whatever you give me, I've got my table, I can just look it up. Let's see, how much time do we have? So I will all right, so okay, I'll maybe tell you about this and we'll skip over the example for now. Example 19 on page 53 in the book is, let's look at number 1, which is P or Q if and only if not Q and not P. And I'll show you the truth table. So this is the truth table for that expression. This is P or Q if and only if not Q and not P. And so they go through this process as well, where first we look at what's P or Q. We can write that in the truth table. We know that information already. What's not Q, what's not P, what's not Q and not P. And so we pull that from there. And so we just compute and for those two columns. And then we compute the biconditional. We have the biconditional information from a truth table. So make sure you know that as well. And this just so happens to give the whole statement a truth value of false, right? So when we compute all of these, it's going to give us false for every single one. So for every possible value of P and Q, this statement is false. This is what we call an absurdity. An absurdity is where every possible truth value for a statement is false. Where I have made a statement, there's no way it could possibly be true. There's no combination of inputs where this statement becomes true. That's an absurdity, which kind of makes sense because I have made a statement that is absurd. Another possible kind of statement is this guy, which is, this is P and not P implies Q, which is also just written here. And this gives us a value of true for every possible input. This is what we call a tautology, which is every possible input is true. Yeah, tautology is like, I have said something that is like just duh. So it's obviously true for any possible input. Absurdity and tautology. So I encourage you to practice for the exam to do all of these examples. So if you don't look at the solutions and you just go to the, like, if you look at these logical statements, write out the truth tables and then compare your answers and see, did you get it right? Question?
For the exam, the solution you're looking for is either absurdity or tautology, or are you looking just for the truth table and
Probably just looking for the truth table. So absurdity and tautology, those are special terms that we use to describe when this sort of thing happens, or when they're all true. But yeah, the truth table is what I'd be looking for, and the correctness of the truth table. All right, other questions? Great. Let's talk about set identities. So sets are, we kind of can describe them in the logical way, like we do with logical statements and propositions. There are some laws and important theorems that we need to be able to know. The book goes through and proves some of them. I don't know that we quite have time for that. But the important thing to know, let's just talk through each of these ones. So first we have the commutative laws. And the commutative laws say, now we're working with sets. And so if I have A union B, that's going to be the same as B union A. And if I have A intersect B, that's the same as B intersect A, right? Commutative, which is we can swap one with the other and we get the same result. Let's actually prove one of those really quickly. So let's say we have we want to prove that A union B is equal to B union A. Okay. So let's start with our proof. And so we can't assume both sides of the equal sign. So do you want to choose left or right? I don't think it matters in this case. Left. Let's do left. So suppose A, okay, so we're looking at A union B. So suppose, if I said suppose A union B, that's not really a statement. Like, I don't really know what that means. So maybe consider is a better word. So we've got A union B. Let's look at something in A. So if A is in A, then A is in, it's supposed to be lowercase A union B. And similarly, if B, lowercase b, is an element of set B, then the element B is a member of A union B, right? That's the whole point of union. These are also, this is kind of where like it's such a simple proof that it's maybe not quite as rigorous as we would like it to be. But A being an A is also a candidate for it being in B union A, right? That's again by the definition of union. And similarly for having something in B. So these are both obviously true. So once we get to this point where we've got something in, so we've got something in A union B, and we've got something in B union A. And so this is for any element in A union B. That element is also in B union A, right? So we're thinking at the general level. We're not thinking of it, like, let's just consider one individual element. We're considering any possible element. And so since we've said this for any, this means that A union B is a subset of B union A. And so now we can flip it. So now if we consider some value x in B union A, we know that x is going to be either in A or B. So X has also got to be in A union B. And since an arbitrary element in B union A is also in A union B, then B union A is a subset of A union B. And remember when we talked about subsets and the proper subsets and equality, once we show that some set is a subset of another and the other way around, those sets are equal. And so now that we've shown this and we've shown this, then we can say A union B is equal to B union A. So each of these properties that we have, we can prove. So we don't have time to prove all of them. But we've got the idea of we can swap unions and intersections. Associative laws, we can move the parentheses around. Excuse me. Distributive laws are kind of interesting. So A intersect B union C means we can have that equivalent to A intersect B and A intersect C. And then we can flip that, where we can say A union of B intersect C is A union B intersect A union C. Complement laws. So this one is kind of our obvious one, where the complement of A is A. And so if we have our Venn diagram, or the complement of A complement. So if we have A complement, which is just the rest of the universe, and we take the complement of that, the only thing that's not filled in is A, and so that gives us A back. This one can be useful, so A minus B is equal to A intersect B complement, which kind of makes sense. Where if we've got A and B, it's just another way of writing it, right? Where we can say it's writing set difference as a matter of unions and complements. Just a way to rewrite it. If we intersect A with its complement, we get nothing, because if we take everything but A intersected with everything in A, there's no in between. And then if we union everything in A with everything outside of A, we get everything. And then we've got De Morgan's laws, which this is also, I'm not sure when we're going to get there for logic, but I will tell you. So this is saying that the complement of A intersect B is complement of A union the complement of B. And so it's this idea of when we negate this whole sentence, it kind of gets distributed and the sign gets flipped. The operation gets flipped. And so this is not P and Q. That's saying this is equal to not P or not Q. So the not bit gets distributed, and then the operation flips from an and to an or. And then similarly for the other case, so not P or Q gives us not P, and then the operation flips, and not Q. So that's what we get. All right, we've got maybe 5 minutes. Any questions on that? I might ask you something about De Morgan's laws. I have to write the exam by Wednesday, so if I do have a question, I will bring it in on Wednesday for practice. All right, let's do some practice problems while we've got some time left. Let's look at, this is number 2 for section 3.6. This is page 57 in the book, in case you're curious. And so let's practice with the truth tables of breaking it down. So start with, we might only be able to get through A. So work on that with your neighbor. Could, but if you, yeah, so do the truth table strategy of solve the inner bit and then not this parentheses. Like if you already know what all the possibilities are for the parentheses, then you just flip all those values. Okay, I'm gonna move us over. Yeah, I ran out of space.
The second easiest one, not P, Q, or P, not Q.
All right, we are out of time, so this will be our warm-up for Wednesday. So make sure, jot down any last thoughts that you've got. Look at the study guide, practice problems, let me know if you have questions. Is there homework this week? Yes. Homework 3, which should also help you study for the exam. My goal is to have homework 2 back to you by Wednesday. So my goal today is to grade it. So if I don't have your homework 2, make sure that you give it to me. All right, see you Wednesday.
Do you have the solution for that?